My name is David. I work as a software engineer at Iterative.ai. And this slide is not showing. So the idea here is that I will try to share with you what's MLOps, in my opinion, because I don't think that there is a universal definition of MLOps, unfortunately. I think it's very dependent on the use case, so I will try to share my experience and how I got into the MLOps world before joining Iterative when I was working as a computer vision researcher in a research center. So, like I say, I was working as a computer vision researcher, and we didn't care about software engineering, best practices, or DevOps. And MLOps wasn't even a word back then. But eventually, our bosses started to worry because the models we were producing were kind of a mess in order to be reproducible. It was the boom of deep learning in our defense. So we were struggling with the deep learning frameworks, implementing new architectures and trying to get the models to train. So we didn't have much time to worry about these kind of things. But as the field of deep learning kind of started to consolidate, we could start paying more attention to the software engineering and the DevOps best practices. So for some reason, I became a good candidate to be the one in charge of embracing this new term called MLOps. So I tried to go around my colleagues, ask questions, and try to define what we need from this MLOps thing. So I asked around, I asked also to myself, what were the main pain points when we were developing models? And most of us researchers agree that the main issue was that taking over a project from other researcher that has left the company, for example, it was very cumbersome. It was very complicated to find all the configuration, data, model, pipeline setup for a project. And this was consistently happening across all projects. It doesn't matter if the researcher tries to actually make it reproducible. We didn't have the tools. So when we were discussing what we want from MLOps, this was the first goal that we would like to cover. And then there was like the extended version of this, that it would be great if this whole manual process of generating models could be automated somehow. Ideally, if I go on vacation 1 week and new data arrives, the model could be trained easily or even automatically without manual intervention. So researchers can focus on doing the actual research instead of manually triggering pipelines. So we have our goals clear, but now we needed to implement this. So we started the quest of exploring the different MLOps tools around. The first thing we jumped into were these cloud providers and end-to-end machine learning platforms by Azure, Google, or Amazon Web Services. And it makes sense that, to be the first thing we try, because we were already customers of these cloud providers for other things, mostly for managing software engineering stuff, but also for hosting data. So the problem I found, I personally found with these solutions were that they isolate the researcher from the software engineering stack or of tools. And ideally, I would like that. I thought that MLOps would be a nice way actually to make researchers closer to the software engineering world, not isolate them further, which we were already very isolated. It was, in my impression, there was also kind of overkill for many projects. We have some projects where it makes sense, this scalability, but we also have like a lot of prototype or proof of concept projects where this setup was completely overkill. And the issue we found is that these platforms, it's not easy to opt out for some of the features. It's like you pick one platform and you have to buy the full pack. And then, mostly because it's their business model, once you start building around your stack around one of these cloud providers, it's very easy to switch. It's very hard to switch to other one or even integrate. So an alternative to this is to go and explore. Sorry, my next slide. Yeah, go and explore the open source ecosystem of MLOps tools. And the issue we found is that this a really vast ecosystem with a lot of tools. There is no clear path there is no explanation of which tools do you need for your use case, how to connect those tools. So we were dancing around, trying different tools and trying to figure out how to connect them. It was not a very pleasant experience, and I think the ecosystem nowadays is still kind of the same. There are 5 tools doing pretty much the same thing for every single part of the MLOps, and this is a not very pleasant experience for users. So we took a step back, and I went to the DevOps team, which we have as part of the company, and asked them, okay, if you do DevOps for software engineering, you seem to have all this figured out. Why cannot we apply the same tools for our machine learning projects? And most of the answers were very similar. I am quoting here a blog post by Baloja, which states the difference between DevOps and MLOps. And the main point is that in machine learning, you actually need to version data parameters and models in addition to code. Whereas in DevOps, traditionally, you only need to version the code. And usually these tools used for software engineering, like GitHub or Git, are not suitable for versioning large artifacts or parameters or models. So we found this tool, which now I work on, which is called DVC, Data Version Control, which is focused on covering this gap by extending the power of Git and GitHub. So it allows you to track large artifacts while still using your traditional software engineering stack. Then the second point was that we were training computer vision models, which are pretty hardware demanding. And usually in the CI/CD world, the machines are not powerful enough for this kind of task. So we also, by the same company that I now work on, which is called Iterative.ai, there was this other solution called CML, or continuous machine learning, which allows you to inject powerful cloud instances as part of your CI/CD workflow. So the training of the model can be detached and launched in a powerful cloud instance with GPUs, for example, or multiple GPUs, but you can still orchestrate and manage the workflow through the CI/CD stack, like GitHub Actions. All right, so usually I use this material for a in-person workshop, and there are 2 links here for the initial version of the workshop where there is nothing done, and there is also a complete solution. So I'm going to go through the slides showing all the steps of the workshop, but if afterwards you want to fork the link at the top and try to follow the steps yourself, and you have the link at the bottom with the final solution. The idea that I wanted to showcase in this project was a prototype for an automatic issue labeler. So I work on the DVC repo, and we have a lot of issues being open every day. And we have to manually assign labels to triage them, to organize. So it sounded like a cool project to have a machine learning model that takes the issue title as an input and can output one or predict one of the labels that we use to categorize the issues. The idea is that we are going to manage everything in a single repository. On the left, we have the data source, which in this case would be the DVC repository, from which we are going to fetch issues with the title and labels assigned in order to build a dataset. We are going to use the tools that I mentioned before, DVC and CML, to build this minimum MLOps workflow around GitHub actions. Then we train a Hugging Face model. And at the end, we are going to pack the model inside a Docker image that can be deployed anywhere. And as an example, we are going to deploy it as part of a GitHub workflow that can automatically assign a label to an issue. So the initial state of the whole workshop, the one that is already included in the non-solution repository, allows us to have what I call local reproducibility. So this is basically that something works on your machine. So as long as you have access to your machine, everything works. In this initial version, we have a DVC pipeline, which is just a connection of stages depending on the dependencies and outputs. It looks like this. We have an initial stage called get data, which gets the issues from the DVC repository and builds and store them in a format suitable for training. Then we have a split into train and validation steps. And into train and validation splits, we train with the train and validation, and we evaluate with the test split. So what I liked originally from the DVC pipelines is that they are non-intrusive. They are defined in a YAML file, but you don't have to alter your code, the code of your stages. So you have at the top level, you have a field called CMD, where you indicate what you want to execute as part of the stage. In this example repository, we are always running Python scripts because just is the thing I like. But the flexibility of DVC is that in this CMD, you can actually call any CLI tool, and you can mix in the same pipeline. You can run Python scripts, run arbitrary CLI tools, whatever you want, without having to modify the actual Python code in this case. The way DVC builds the graph of stages is by indicating dependencies and outputs. So you tell DVC that there is a file or a folder that you want to consider a dependency of this stage, and you already there's another file that this stage is going to write. So after you get this, so to indicate to multiple stages, DVC builds the graph that we saw in this slide based on the disconnection of dependencies. This is how DVC allows to build a pipeline without actually requiring you to include any code in your existing stages. There's also some additional machine learning features, these kind of special outputs called metrics and plots that are useful for DVC to later rendering. So having the pipeline, if I am on my machine, I can run this command called DVC experiment run, and I can even modify parameters on the fly. And because I have a local DVC cache, DVC actually checks if some of the dependencies have changed or not. So in this case, the two first stages don't have any changes. So DVC is going to skip the stages and just retrieve the outputs from the cache. But because I modified the parameters that affect the train stage, DVC actually recomputes the train stage and the evaluation stage. So this is how it looks, a high-level diagram of how is this local setup. I have my code, and I have some special metadata files that I track with Git. So I can run git pull and git push commands. And I have a local cache, that's why I can reproduce the pipeline locally, where DVC actually stores the big data files. and it maintains a link between the metadata and the actual files. The problem is that I can run git push to share the metadata and the code, but I am missing a way to share these big data files. So this is the next step that I call share reproducibility. Before that, after you have set up all this DVC pipeline, we just launched this free extension for Visual Studio Code, where these special outputs that were in the stage like metrics and plots can be actually rendered as part of the Visual Studio Code UI, and you can run experiments from the Visual Studio extension. It's pretty much a wrapper of the DVC CLI, but it has a nice dashboard and features without requiring you to launch an external server. This just works on your machine using the DVC artifacts. So now, jumping into this next stage, which is called shared reproducibility. So what we need to do in order to fill the gap that we had before is to include this thing called DVC remote. A DVC remote can be an arbitrary cloud storage that allows you to run these new commands called DVC pull and DVC push. So you can pretty much mimic the workflow you were following with Git, but now you additionally need to run DVC push and pull to actually fetch or get the large artifacts from the remote storage. And setting up a remote storage can be as simple as you want, and the commands are the same no matter which cloud provider you choose as remote storage. One of the simplest one is you can actually create a Google Drive folder in your Google Drive, and you can add that folder as a DVC remote, running the commands at the bottom of the screen. So just by adding that, running that command and creating that folder, DVC is already able to use this Google Drive folder as a remote storage. So if researcher A in his machine runs this new experiment, increasing epochs to 12, and actually tracks the changes with Git, it can now also run DVC push to get these large artifacts, the dataset and the model, and put them in a remote storage. So researcher B, when clones this repository or pulls these latest changes, from Git is going to retrieve the code changes and the metadata changes, and DVC pull is actually going to get these large artifacts, the corresponding that are associated to these metadata files, and going to retrieve them from the remote storage. So now people from different machines can share not only the code and the small files, but also the large files. And these commands work the same for all the remote storage. So you can also use an Amazon S3 bucket, Google Cloud bucket, wherever you want. So going even further, why not use GitHub, where we are tracking our code and our metadata files, to actually run the experiments? And as we mentioned before, the issue is that if we train really large models, the machines that GitHub Actions, for example, provide might not be powerful enough. So CML provides you this utility called CML Runner. And the way you use it is that you insert a step in your GitHub Actions workflow called CML Runner that can trigger, can create a new cloud instance in any of the major cloud providers, Amazon, Google, and Microsoft. You can set up, you can customize which kind of machine you want, and then the rest of the workflow can pretty much do the same steps that you would be doing locally, but instead of running locally, now it would be running in this cloud instance that CML has taken care of creating and will take care of shutting down after the subsequent steps have ended And if there is a failure, the instance can also get shut down. So we are pretty much using the same tool, GitHub Actions workflow in this case, that we use for testing and linting our code, but now we can also use this tool for training our machine learning model. After we have added this workflow in our repository, we can create a PR updating some of the parameters, and CML is going to run all these steps. CML is going to create the cloud instance as a first step, and then it's going to run this DVC pull, DVC experiment run, and DVC push commands on that machine, which is pretty much what we did locally. And it's going to take care of creating a PR with all the metadata files, all the files tracked by Git. And it also provides some utilities to actually generate reports of the experiments and post them as GitHub comments, which is the screenshot that I show on the right. So this is all happening through GitHub or GitLab Orbit bucket, by the way. CML works the same for any of the Git providers. We also provide this free to use up to 5 or 2 users. I don't remember. I think 2 users, which is called Studio. It basically allows you to connect your GitHub repository to this SaaS called Iterative Studio. And this provides you a high-level overview of your repository, recognizing these special metadata files for DVC, like the parameters metrics and DVC track files. And it also allows you to trigger new experiments from the UI. So when you click on run a new experiment, it's actually going to create a PR on the GitHub repository that you connect. And that PR is going to trigger the workflow that we define at the beginning of this section. It also allows you to compare different commits after you have been iterating with different hyperparameters, for example, trying the number of epochs. This Iterative Studio, similar to how you can render the plots and metrics locally with the Visual Studio extension, you can do the same here. Do the same here in the website in a more shareable way, because you can actually share this view with your colleagues. So yeah, this is Iterative Studio. So this is cool. We are now even training our model in GitHub. Everything is online. Anyone with access to the GitHub repository can trigger a new experiment, but we are missing the step of deploying. Usually when I was working as a computer vision researcher and we find like the next good iteration of a model, we either grab the model in a Docker container and wait for someone from the DevOps team to come to deploy it, or we actually did some crazy stuff, sending the model through Gmail or Slack or something like that. So in the repository, we can actually do the same step, which is building a Docker container that wraps the model with an inference script. The interesting part here is that we are copying the actual model inside the Docker image, right? So because DVC with the remote storage allow us to pull and push these big data files, inside the GitHub Action workflow, I can actually run DVC pull command to get the model, so I can reuse this popular GitHub workflow for building and deploying Docker image, and I just add this additional step where I am actually getting the latest version of the model from the DVC remote that one can that could be pushed by someone locally or could be pushed by this pull request workflow that we added. It doesn't matter because the workflow works the same. So this workflow is going to build a Docker image, is going to publish the Docker image in the GitHub Docker registry as part of the as part of our GitHub repository, we can host Docker images. So if we pick this workflow and include in the repository, every time a new commit gets added to the main branch, for example, when a new PR gets merged, this workflow is going to be triggered, is going to fetch the latest model that is pushed in the DVC cache, and is going to create a Docker image with the latest model available for anyone to use. So you no longer have to wait for this slow process of having to share the image with someone manually. And as an example of how you could use this image, as part of the workflow, I create this yet another GitHub Actions workflow that whenever a new issue gets created, is going to pull the Docker image from the main branch, so the latest version, is going to run inference over the issue title, and is going to store the result in a JSON, and then we just did some little trick to pass the JSON and actually automatically assign the label. So if you go to the solution repository and you create a new issue with an example title like this one, a GitHub Actions workflow is going to try to fetch the latest version of the model, predict a label, and automatically assign it. So this is just to showcase an example of how you could deploy a model, but depending on the project, you could do it the way you want. For me, the important part is that thanks to the DVC remote, I can actually reuse this workflow traditionally used for building Docker images, and I can insert an additional step to retrieve interesting artifacts from the DVC remote. So with that, the model is deployed. And the last step is just that because we are using GitHub Actions workflow, we can exploit the capabilities that they offer for orchestrating and triggering actually workflows. So the workflow we added in the online reproducibility step was either manually triggered or triggered when a new PR gets created. But we can also use the GitHub Actions features, which provides a cron job to automatically trigger a workflow on schedule. So if we add this, we pretty much copy paste the same pipeline that we are using in the online reproducibility, but we tell GitHub to trigger this workflow at the end of it, at the beginning of each day. And then we can also use these features by DVC experiment run, where you can modify parameters on the fly to actually update a parameter. So in this workshop, I have two parameters, data since and data until, to control the boundaries of the dates to fetch issues from. So what I am doing here in this automated workflow is that at the end of each day, I am going to trigger and train a new model, which is going to use a new dataset because it's going to fetch issues not only from the previous boundaries, but it's going to increase the boundary of until to the current date. So every day I'm going to fetch the latest issues from the GitHub DVC repo. I'm going to train a new model with a new dataset, and the whole other steps like creating a PR, generating a report are also triggered automatically. So I can decide if I want to merge this workflow or not into the main branch. I could even automate the branching, the merging, by checking if the accuracy has surpassed some threshold. But yeah, I don't want all the researchers to be fired, so it's still good to have a manual step of verifying if the results are actually better or not. And this was actually faster than I thought, because I think I have finished, and I can share quite a few links for helping you. So please don't hesitate on asking any questions. I will try to answer.